The standard cosmological model, lambda CDM, has a problem. It struggles to explain the rapid formation of the very first stars and the massive scale of early supermassive black holes. Independent researcher Nathaniel Faxon Sharir, who balances his days conducting astrophysical research and his nights working as a food sever, proposes a distinct solution. By looking past the standard model's reliance on unverified dark matter, Sharir's framework provides a mathematically rigorous explanation for these early cosmic anomalies. This is the Cosmic Helium Evolution Theory, or CHET. The first component shown here is the galaxy formation equation, which calculates galactic mass and structure. Below it sits the star formation equation, mapping the exact birth rate of massive stars in the early universe. Finally, the black hole growth equation models the mechanics of rapid mass accretion. Across all three equations, one specific variable dictates the outcome: rho He4, the density of primordial helium-4. By isolating this single variable chronologically, the framework resolves the timeline of early universe formation, eliminating the need to rely on missing or invisible matter. To test this math, we look to the Y1 galaxy, positioned exactly 820 million years after the Big Bang. Y1 operates at a staggering star formation rate, producing stars 187 times faster than our modern Milky Way. This extreme velocity is mathematically driven by high cosmic web density, colliding with extreme levels of primordial helium-4, forcing violent core ignition. The resulting helium-rich stars are immense, ranging anywhere from 1 to 1,000 solar masses. Their individual life cycles dictate the structure of the surrounding galaxy. Stars between 1 and 50 solar masses collapse directly into black holes. Intermediate stars, spanning 50 to 150 solar masses, end in standard supernovae, leaving black hole remnants behind. Hypomassive stars, exceeding 150 solar masses, bypass the supernova phase entirely. They are mathematically guaranteed to collapse directly into intermediate black holes. Primordial helium-4 dictates a distinct, accelerated stellar life cycle. It forces the early universe to aggressively and silently seed itself with massive black holes. We can observe this direct collapse mechanism in the modern universe. In 2014, astronomers monitored a specific event in the Andromeda Galaxy, designated M31-2014-DS1. A 13.2 solar mass yellow supergiant simply vanished. It collapsed directly into a 5.2 solar mass black hole without emitting a supernova flash. Based solely on the star's local helium-4 abundance of 0.031, the CHET framework predicted this exact outcome with 99.97% accuracy. Once these black holes form, they enter a rapid growth phase governed by a modified Super-Eddington Accretion equation. Factoring helium-4 density into the mechanics of this accretion process reveals an exponential boost to standard growth rates. This graph plots the accretion rate against helium-4 density. As density increases, radiation pressure saturation creates a hard physical limit, plateauing sharply at a density of 0.35. At this exact threshold, the accretion rate increase is permanently capped at 620%. This mathematical ceiling prevents runaway, infinite growth, while cleanly explaining how supermassive black holes attained such massive scales so early in cosmic history. This framework also recalibrates our understanding of structures like CDG2, a galaxy traditionally classified as being composed of 99% dark matter. The galaxy's halo appearance matches mapped neutrino density distributions. While neutrinos only account for 1% of the total mass, their density gradient perfectly mimics the fuzzy visual signature typically attributed to a dark matter halo. The actual gravitational discrepancy is entirely explained by a dormant 200 million solar mass supermassive black hole located directly at the center. A total lack of incoming matter deprives this black hole of standard visual accretion markers. It remains magnetically active, but entirely dark. Although standard Hawking radiation for this mass is negligible, CHET shows that enhancements in the black hole's spin and charge generate a thermal output of 10,000 to 30,000 Kelvin, perfectly matching the previously unexplained temperature anomaly in the galaxy. The phenomena assumed to be dark matter in CDG2 are the measurable symptoms of early universe helium abundance and central black hole dormancy. We can confirm this dynamic by looking at a negative control case. Cloud 9 is a diffuse cosmic structure containing 5 billion solar masses. Despite possessing more than enough raw mass to ignite, it contains 0 stars and 0 black holes. Applying the CHET framework to Cloud 9 reveals a complete mathematical absence of helium-4. Without the primordial helium-4 catalyst, all star formation mechanisms are mathematically suppressed. External factors, including magnetic fields and plasma jets from neighboring galaxies, introduce turbulence that further prevents dense core collapse. Cloud 9 demonstrates that sheer mass is insufficient to spark stellar evolution. Primordial helium-4 is the necessary catalyst required to transition a gas cloud from a diffuse state into an active stellar factory. Zooming out to the macro scale of the cosmic web, the predictive power of the CHET framework becomes clear. This table details the equation's performance. They have achieved greater than 99% predictive match rates across multiple distinct, highly distant targets, including Y1, GNZ11, and the early red dots. By tracking a single variable, helium-4, we calculate star life cycles, define absolute accretion limits, and map galaxy morphology, all without invoking missing matter. This mathematical framework operates in strict alignment with deep-field observational data pulled directly from the James Webb Space Telescope. To explore these proofs further, please return to MDU. If you found this analysis valuable, please like and subscribe. We extend our sincere thanks to Curt Jaimungal for the #Core1 initiative, fostering the exploration of fundamental theory.